Hello everyone, my name is Aaron Klimas-Swartz, and today I will be talking to you about part of my ongoing master's thesis work at the University of Manitoba under the supervision of Dr. Dirk Wyrick. When I think about my daily life, I often find myself spending as much time as possible outdoors. Before I venture out, I check the weather, and more specifically, I check the temperature. I want to prepare myself for the day by either bundling up in the winter months to protect myself from the cold, or choosing to wear less layers and taking advantage of the hot summer days. But not all organisms have such luxury. Specifically, when we look at aquatic ectotherms, we know that they are incapable of thermal regulation due primarily to the energy constraints associated with heat loss. John R. Brett and F.E.J. Fry described environmental temperature as an ecological master factor, meaning that temperature plays a dominant role in an aquatic ectotherm's behavior, physiology, and life history. One way of looking at the interactions between temperature and aquatic ectotherms is by looking at an organism's thermal tolerance. All aquatic ectotherms have a limit to how hot or how cold their environmental temperature can be. The thermal tolerance of an animal is defined as the range of temperatures an organism can live in by changing its behavior or physiological processes. For my master's thesis work, I wanted to investigate the thermal tolerance of northern crayfish. I chose to work on northern crayfish because they occupy a large geographical range within Canada and the central United States, and they represent a keystone species within our local freshwater habitat within Manitoba. The specific population of crayfish that I collected all came from the man-made stream called the Red River Floodway. The floodway was designed to protect the city of Winnipeg from rising floodwaters from the nearby Red River, and as a result, it often experiences changes in water level and temperature. For instance, during my field collection, I documented a change in water temperature of 4.5 degrees in just 6 hours. Previous research done by Dennis L. Clausen documented the critical thermal maximum of northern crayfish to be at around 38.5 degrees. However, I was more interested in assessing the physiological changes in northern crayfish after a long-term acclimation to a variety of environmentally relevant temperatures that the crayfish would experience on a yearly basis. If we look at our current freshwater environment for the Red River floodway, we observe a temperature gradient between 0 and 27 degrees. I decided to represent the entire temperature range for the floodway by acclimating my crayfish to one of 5 temperature groups between 5 and 25 degrees Celsius for at least 2 weeks. My objective was to obtain physiological evidence on the thermal tolerance of northern crayfish and assess its response to the wide range of temperatures. During the acclimation, I monitored all water parameters at least every 48 hours, and all animals were fasted for at least 48 hours prior to any experiments. The first experiment I ran looked at whole animal ammonia excretion rates to quantify the amount of waste being produced by each crayfish. I placed each crayfish into a small container and measured the amount of ammonia in the water after 3 hours using an ammonia plate assay. Results for this experiment show a linear increase in whole animal ammonia rates with increasing acclimation temperature. The crayfish are producing more waste at higher temperatures, but are also able to regulate the excretion process quite well and are certainly capable of maintaining excretion at higher temperatures. The majority of my experimentation centered around measuring the oxygen consumption of each crayfish at my different temperature acclimations. I used an intermittent flow respirometer setup to perform a 24-hour trial for measuring routine metabolic rate and maximum metabolic rate. By using a 24-hour trial, I am measuring the amount of oxygen consumed in northern crayfish in a rested state, as it took at least 4 hours for the oxygen consumption to stabilize once I had placed the crayfish inside the respirometer. To measure maximum metabolic rate, I exercised each crayfish for 5 minutes by forcing them to swim within a water bath. Crayfish were deemed exhausted when they no longer tried to swim using their tail for at least 1 minute. After exercise, I immediately put them back inside the respirometer and ran a single trial to measure their immediate response. So results for routine metabolic rate showed that the crayfish are capable of increasing their oxygen consumption at higher temperatures. Interestingly, the crayfish at 5 and 10 degrees have a similarly low rate of oxygen consumption, possibly due to their lower overall activity. Additionally, there is only a small change observed in the crayfish between 20 and 25 degrees, suggesting that the crayfish may be starting to show signs of a reduced physiological response at temperatures beyond 25 degrees. For maximum metabolic rate, the crayfish is quite capable of acute changes in its oxygen consumption and is also highly versatile in ramping up its oxygen consumption rate at higher environmental temperatures. Interestingly, this response is more linear in fashion compared to the routine metabolic rate, possibly indicating that the crayfish is indeed versatile in changing its oxygen consumption rate in response to aerobic and acute exercise. So taken together, the routine metabolic rate and maximum metabolic rate can be used to summarize the scope of aerobic activity. So this value is defined by Matha Havis and co-authors as the amount of oxygen available for fitness-related traits such as growth, foraging, locomotion, and fecundity. Looking at our results, it is clear that the northern crayfish is capable of maintaining its scope of aerobic activity even as temperatures climb to 25 degrees. Therefore, it is safe to say that the northern crayfish is fully capable of maintaining the high oxygen consumption requirements needed to sustain the energetic demands of living in that environment of 25 degrees for at least 2 weeks. The next parameter I measured was hemolymph pH by taking a sample from the base of the fourth pair of walking legs and immediately analyzing that sample using a micro pH probe. So higher acclimation temperature resulted in a significant decrease in hemolymph pH. So this decrease could be a result from the increasing respiration, contributing to a metabolic acidosis. Additionally, the large range in pH that is observed leads to the conclusion of northern crayfish being able to at least accommodate a substantial change in extracellular pH. My last set of experiments involved isolating the gill tissue from the northern crayfish and measuring oxygen consumption and ammonia production. I used an Ouroboros machine to measure the oxygen consumption within the gill tissue for 1 hour after dissection. Gill tissue ammonia production was also measured for 1 hour. Gill tissue oxygen consumption rates increased in response to increasing acclimation temperature. Additionally, the gill tissue consumed 5 to 17 times more oxygen per unit mass compared to the whole animal. Results of this experiment demonstrate the critical role that gills play in respiration in connection to their function in ion regulation and osmoregulation. Interestingly, the gill tissue ammonia production remains stable across all temperature acclimations. This result is in contrast to the whole animal and provides evidence towards a carbohydrate-rich energy source being used to maintain high oxygen consumption at higher temperatures due to the ratio of oxygen to nitrogen remaining relatively stable. Again, the gill tissue ammonia production is 14 to 85 times higher when compared to the whole animal excretion. So in conclusion, the northern crayfish demonstrates a high thermal tolerance and are able to compensate for high environmental temperatures of 25 degrees for 2 weeks. Crayfish are capable of adjusting their metabolism, excretion, pH, and gill function to achieve a new steady state and satisfy the energy demands of living in warmer waters. Overall, these results suggest that the northern crayfish have evolved the necessary tools needed to survive in the harsh environmental conditions presented to them on a yearly basis. I would like to thank everyone for tuning into this presentation and to thank all of my colleagues, friends, and families for their support. Thank you to my contributing authors, Dr. Jason Treberg, Rex Yoon, and especially to my supervisor, Dr. Dirk Wyrick. Thank you to the University of Manitoba and NSERC for providing the opportunity to undertake this project. And lastly, thank you to the Canadian Society of Zoology for allowing me to share this valuable information with all of you. Stay safe, and I look forward to our interactions during the live discussion period.